Alright, I'm gonna finally put this video out here. I know it's not perfect, I know it's not everything that you could ask for, but it's my first video, and if I'm not gonna put it out now, then I never will. This video is not meant to be perfection. In fact, it is just a really fancy way, I guess you could say, of solving an equation using the animation software Manum, provided by 3 Blue 1 Brown. It has no visual intuition necessarily when it comes to graphs or 3D models or anything fancy. It is mostly what you would see on a whiteboard if you were to solve an equation. And the point of the video is not to be that serious either. It is just a goofy way to solve something that's a famous problem that no one really talks about. And I find that very fascinating. Thank you, Michael Penn. I have been holding off on this first video idea since 3 Blue 1 Brown's first math exposition until my computer died and my entire video crashed about a year ago. And then I went through a time period of not doing it at all. So I'm going to release this. You have to get started somehow, someday, some way, and this is how I'm going to do it. So enjoy the stock footage in the background. I had nothing else to use, and let's get to it. To make this process a little easier on me, I'm going to record my voice while I'm watching the video alongside with you guys. Here is some recommended base knowledge for this. Calculus 1, as long as you know integrals and derivatives, you're on a good pace, and some knowledge about infinite series, and that'd be all. So, sigma notation. I'm going to do a quick explanation for this. Also known as summation in certain situations. There's 3 parts to this: the index variable, lower limit, and upper limit. I got some nice arrows pointing to what means what. You'll never need to know this information again in your life, but once you get used to it, you'll know what it means forever. Let's change that K to an infinity sign. What happens then? Well, first let's introduce the Basel problem. There it is. The 1 over n squared from n equals 1 to infinity. And here I play a little nice animation of me, a little too slowly, writing out what this would look like. Obviously, my computer isn't from the future, and it will not be able to show you what infinity looks like here, but I do go up to 9, and I insinuate that it continues, because it does. It continues forever and ever and ever, and that's the pretty thing about it. Here's the shocking thing. It equals pi squared over 6. Isn't that bizarre? So I whipped up another animation. I was very proud of this about 8 months ago when I first did it, of n going up to 500. Here you can see that the 1.64 starts to stay constant, and eventually it looks like that 2 starts to stay constant too. It doesn't. It goes past the 2. But you can see that it's definitely narrowing down to a point. And if you were to look at pi squared over 6, there it is. Let's talk about convergence versus divergence. A short summary. Thank you, pass me. So, if the summation from 1 to infinity of a sub n equals infinity, it diverges. It does not resolve into a finite solution. You cannot label it by a number, and vice versa. And that would be convergent. So the summation of 1 over n squared. Let's write it into 2 separate parts. And let's label on the number line alternating blue and yellow. Now, why would I do that? Well, the first part of the equation are all the even numbers. The second would be all the odds. Combine them together, and you have the original full equation. Now here's some algebraic rewriting. Not going to explain it in real time, but that's what do you do. You'll get there, and you'll come across the thing at the very bottom. Let me unwrite some stuff and, you know, do that fancy animation, because I thought that would be a smart idea. We need to go off topic. So let's solve this integral. From 1 to 0, x to the power of b times the natural log of x dx, using the classic integration formula. Here, I will let this animation play through. Basically, if you understand how this integration formula works, you'll know what's going on. It can take a few steps, and it is fairly confusing because there are a few things that technically equal negative or positive infinity, and if you know what to do, you can cancel everything out. But I'll let this awkwardly transition, because I did not know how to use a transition method originally, into the final solution of 1 over quantity b plus 1 squared. And that's what it equals. Now there's a relationship between these two highlighted objects and the signs right there, the positive and negative. Now, how can we change it into looking like it? And there we are. It's a little complicated, but here's a dog break. While you are looking at this golden retriever, if you feel at all confused or rushed, that is my fault. The animation is way too quick. However, you can always go back and pause at certain points, and you can always also go to Michael Penn's video that I put in the beginning and take a look for yourself. But just take a deep breath, and we're about to walk right back into the next section of this. So let's do a recap. The summation from 1 to infinity of 1 over n squared equals 4/3 the summation from 0 to infinity of an integral. Not very user-friendly, is it? However, we are going to take a look at this as well, and we're going to get through this together. Here, we use some general rules of summation and integration, where in certain cases, swapping is allowed. Here's a video from Bree the math guy explaining a great concept of it. Here's a few notes on the side. Certain things that'll help us throughout our process here. And there's our first substitution of that integration right there. We replace that summation into 1 over 1 minus x squared. And now, maybe make that natural log of x look a little more complicated. And here is the same way you can write that upper subtraction of those two natural logs into a way of describing it with limits of y. And here we're going to use a trick where we basically integrate and derive at the same time for the same value. I mean, now we're going to do some solving. Again, I am so sorry for how these transitions look. Here we are. It's scary, but we got this. Take it slowly and look through every step as you wish, and pause as many times as you would like. Now we have double integrals. We're going to do some rearranging right there. We let u equal xy, u squared equals x squared, y squared, dx equals 1 over y du. And now we're in the u world. And this is the final stretch, ladies and gentlemen. Even some more substitution, and we are at the last stretch right here. Four-thirds times the integral from 0 to pi over 2 of u du. Do some simplification, and there's our final product, pi squared over 6. And that equals summation from 1 to infinity of 1 over n squared. Here is the most complicated solution to the Basel problem. So I'm going to continue staying off script like the rest of this video was. I would like to thank anyone who stuck around towards the end. I know it'll probably be the friends and my mom that I sent it to originally before anyone else sees it on this planet, but it really means a lot to me regardless. I think this video will be nowhere near my best, and I understand that, but like I said in the very beginning, I needed to get this out or else I'll never get started. I understand at certain points it went incredibly fast, and I will definitely take that into consideration when I create my next video, and I do have a few more animated videos coming up. I am also very willing to do other stuff that doesn't require any animation and requires actual video footage and explanations and going to weird places and stuff like that. I really enjoy channels like Tom Scott and Veritasium and Vsauce and 3 Blue 1 Brown, Minute Physics. I mean, I really like all that nerdy science stuff, and I want to get my foot in the door, and I want to be one of the guys with them. Regardless, I'm gonna work on these videos and make them a lot better. And this video was my first ever attempt at really using Manum as an animation software, and I believe that I did a good job for what I did. I'm not ever going to show anyone the code because it's absolutely god awful. I'm assuming it's got to be like spaghetti code, but I made it work, and this is the final product, and that's all that really matters to me. So have a good day.